Okay. Hello, everyone. The title of my talk today is Optimizing Energy Consumption and Performance in Modern Cloud Systems. A bit about me. I completed my PhD in University of Technology of Terroir. My thesis title, Enhanced Cross-Layer and Secure Architecture for Connected Vehicles. After that, I held several postdocs in Telecom Paris. And my first postdoc analysis of machine learning algorithms for detecting DDoS attacks in connected cars. This project was funded by Connected Cars and Cybersecurity C3S. And my second postdoc addressing latency and security challenge in V2X. This project was in collaboration with COA and funded with Inter-Carnot versus Share project. Currently, in my postdoc about cloud network systems with energy performance constraints, funded with Pepper project. In this presentation, I will start by introducing the context, motivation, and goal of the presentation. After that, I will introduce the background of cloud network infrastructure. I will address energy footprint, the component factors and measurement. And then I will talk about the strategies for energy efficiency. Ending my presentation with a review, case study, and practical application. Cloud networking involves designing, deploying, and managing network infrastructure that support cloud services. Cloud networking includes hardware, software, and protocols to connect and manage distributed cloud resources. Cloud networks are expanding to support more servers for AI, big data, and IoT. Data centers require substantial energy to power and cool equipment. A large data center can use the same amount of electricity as 80,000 homes in US. And this figure shows the increasing of power consumption in US data centers from 2022 to 2030. By 2030, power consumption from data center in US projected to nearly double, reaching about 35 gigawatts, up from 17 in 2022. This expansion contributes to a large footprint and higher operating costs. Reducing the energy consumption helps manage cost and sensibility goals. So the challenge is how we can optimize the energy efficiency without compromising the performance of cloud services. Cloud infrastructure. The cloud infrastructure components are servers, storage system, network equipment, power supplies, and cooling systems. Example of daily action consumption. I will take example about shopping in Amazon. Every action involves computing power, storage, network, and networking to ensure seamless shopping experience. For example of actions, searching for a laptop, impact database, large computing. The second action, recommendation displayed, real-time machine learning, which impact the GPU. The third is the product click, which retrieves from storage system, which impact the contact served in storage cluster. Add cart, which impact the synchronization service and database. Place order, impact that distributed systems optimize, post-purchase email and tracking send impact the background job in data centers. My goal in this presentation is to present what is energy footprint and what are the main strategies discussed in the literature to decrease the footprint and the cloud infrastructure. Energy footprint refers to the total energy consumption associated with running a cloud infrastructure, application, and data processing activities. The component of energy footprint, the computing resource, power used by servers, storage, and network device, the cooling systems, data center require extensive cooling to keep the server from overheating. Supporting infrastructure like UPS and lighting also contribute to the overall energy footprint. Factors that affect an energy footprint. First of all, the hardware. The choice of hardware directly influence the overall energy footprint. Also, the cooling technology. So an efficient cooling technology can increase the energy consumption by requiring excessive power to maintain stable temperature. Workload management. So poorly workload management can raise the energy footprint. And in workload, there's also several factors that impact that. The power and balancing, increased data transfer, ignoring scheduling, and frequent scaling. Energy footprint equal to the summation of energy of computing servers, virtual machines, energy of storage used for data storage, and energy required for network equipment like router, switch, and data transmission, energy used for cooling systems, and energy consumption like power supply and backup generators. Striking a balance means optimize energy efficiency with the performance needs. This is a challenge due to many reasons, including unpredictable workloads, variable demand and latency sensitive application creates schedule challenge, and the complexity in distributed systems. Coordination across the cloud, edge, and local devices. Strategies for energy efficiency. 3 key strategies have proven effective in building energy efficiency, high performance in cloud environment. The first one is the resource consolidation. Resource consolidation means that we want to reduce the number of active servers. Workload orchestration, dynamic management of workload, and intelligent offloading by shifting tasks to efficient locations. The first strategy, resource consolidation, is the process of reducing the number of active servers required in data center to a fewer physical servers or virtual machines. So with the fewer active servers, there is a lower cooling demand, further decreasing the energy consumption. Many levels of virtualization in cloud computing exist, such as network virtualization, storage virtualization, and server virtualization. There are 2 main types of server virtualization: VM-based virtualization and container-based virtualization. In the first one, A virtual machine is a software-based emulation of a physical computer which runs an operating system and application just like a physical machine. Physical resources are virtually distributed at the hardware level through a hypervisor. A hypervisor is the management layer that manages and control all VMs. The most popular hypervisor worldwide include VMware, Oracle VM, and others. In the containerization, the containerized environment comprised a container engine and any number of container instances. All containers are hosted on the same machine and share the OS kernel, including the root file systems, libraries, and common files. Many providers expose container services such as Google Container Engine, Docker, and Amazon Elastic Container Service. The second strategy is the workload orchestration. Workload refers to the tasks or services that must be managed. Data flowing these components is considered part of the workload. Orchestration is the automated process of coordinating, deploying, and managing workloads across multiple resources in cloud environment. It aims to ensure that workloads are efficiently distributed and meet performance requirements. The benefits of workload orchestration: first, the energy saving. Resources are only used when necessary, reducing the ideal time and power consumption. Performance optimization: orchestration workloads maintain high service quality by responding to demand fluctuations, ensuring minimal latency and resource waste. And in the scalability, workload makes cloud environment more scalable and adaptable. Kubernetes. Kubernetes is an open source container orchestration platform created by Google in 2014. It offers the following functionalities: service discovery and load balancing. In the service discovery, detects services and distribute load efficiently. And in storage orchestration, manages storage for stateful applications. Kubernetes automates containerized application deployment and management in large-scale computing infrastructure. It relies on container runtime systems such as Docker and is in charge of creating and running container with a group of server machines. A pod is the smallest scheduling unit in Kubernetes. It consists of one or more containers. The third strategy is the intelligent offloading definition. Intelligent offloading shifts specific tasks or workloads to data centers or servers that are more efficient depending on factors load, location, and energy availability. Edge computing. Some tasks are offloaded to edge location, closer to user, to reduce the data transmission energy and latency. In the edge computing, reduce the latency and central resource by offloading data processing to edge device or edge server, which is closer to the data source. Sensitive data can be processed locally on the edge without transmitting it to centralized servers. Use cases: first, the real-time processing application like augmented reality, autonomous driving, and video streaming. The second one is IoT environment, where local devices handle data to make quick decisions. AI and ML in intelligent offloading. We use the historical data and machine learning algorithm to predict future workloads, demands, and energy consumption services. Methods: time series analysis, algorithm usage trend and peak times by analyzing pattern over time. And the second one is the reinforcement learning. Machine learning models continuously learn from changes in workload demands to optimize resource usage. Use case: data centers predicting cooling and power needs. And also we can use AI and ML to workload scheduling, resource allocation, and to anomaly detection. AI optimizes scheduling by analyzing task priorities, deadlines, resource availability. Methods: use case: a cloud service provider using AI to allocate virtual machine dynamically based on demand. Case study and practical application. First, Google data center energy efficiency. How Google data center minimize energy efficiency? Google has implemented several efficient strategies in its data center, such as using AI to optimize cooling and reduce energy. Google's use renewable energy such as solar and wind power to run its data center has also set an industry standard for energy efficiency. Practical application in the individual footprint. Kindly type this link in your browser. Okay, this is an individual footprint for a student studio. I take a studio case. So if you in this practical application, a studio case, it's, the consumption of each individual in studio is a PC, portable, écran, smartphone, mouse, keyboard, and Wi-Fi. And each one, you can choose the duration of each component. And at the end, we can see the consumption electric of each person in 1 year per year. So the studio energy consumption is approximately to 193 kilowatt per year. And in my second example is an office case. Also the office case energy consumption, PC, écran, Wi-Fi, server, and telephone. The energy consumption is approximately to 1290 kilowatt per year. Thank you for your attention.
Does it work? Yes. So from what I got, the most difficult part for this kind of work is to get access to the reliable sources of data, like saying this equipment is going to, with these years of life, is going to cost you that much in energy for I don't know how many operations, right? So I wanted to know if they gave you some access to relevant information or relevant sources of information,
No.
which probably they use to do this calculator.
No, they didn't give. They does not give us the sources. So what I know, it's theoretically how we calculate it, but we do not have a source
Of data.
of data.
Okay.
Yeah, quick question. When you gave the model for the energy consumption at the start, you basically said it's the sum of the consumption of each component, and for each component, the sum of the different energy consumptions. But that model doesn't take into account sort of mutualization and things like that. Are there models that are more precise in taking into account how, for example, workloads are mutualized on the same server so that we know when we do our optimization, when we do our load balancing, how that affects consumption other than just a linear equation which won't move? I'm not sure if my question's clear. Because you have a slide at the start where you say it's the sum.
I can go to the
Yeah.
slides of strategies. Maybe it will be more.
Prior to that, it's the energy consumption slide. Here you don't say, we see how it impacts, but if we were to do optimization, we don't have that formula which says what we're trying to optimize in terms of energy. If you go to the, I think it's one of the earlier slides.
The optimization in the first strategy is it's in virtualization. By reducing the number of physical servers into fewer physical servers. Oh, yeah. The main word in the first strategy is the virtualization. So when we reduce the number of servers, we reduce the number of cooling systems.
Okay, so you assume that the cost is linked to the number of servers, not the number of workloads.
No. Yes.
Yeah.
And the resource consolidation, the global description of is to decrease the number of servers.
Okay. So
they work in consolidation. Maybe if anyone want to any company, and if they want to reduce the energy consumption, they take into consideration the three strategies in parallel.
Yeah.
So they make the virtualization. So they reduce the number of servers. After that, they manage the workload. They manage the workload also by using Kubernetes that manage the services into containers and orchestrated by. And in this third one, they shift the tasks into the effective servers, and so they maybe in order to reduce the energy consumption, we should use these three strategies.
I agree on the three strategies. My question is more, how do you model the final energy consumption based on your strategy? Because you need to know when you're going to try and apply a strategy, you want to know how efficient it will be. So you need to have a model that says, here's my prior consumption, here's my posterior consumption. And so you need some sort of formula which tells you what the energy consumption will be based on your deployment. And that's what I was trying to get at.
Maybe I can go to this slide.
Yeah.
This slide, if this slide contains all the components that used in calculating the energy consumption.
Yeah.
So when we have the number of servers and the number of network equipment, the number of storage. So we can calculate all the energy consumption according to these components.
Okay, and how?
And the virtualization reduce the server and also reduce the cooling system.
And do you know how, for example, is the cost of cooling, is it linear to the number of running servers, or is it more of a more complex equation than just linear? This is the sort of, because that's how that's information you need to optimize properly.
Yes, yes. The cooling system, maybe it's the most the greater energy consumption in all of these. So maybe most of the research reducing talking about reducing the energy systems, because the energy systems cooling systems it consume more than network equipments. And so maybe I mentioned this in the last slide about Google data center. The Google data center use renewable energy such as solar and wind power to run its data. This using of solar and wind power reduce for cooling systems.
I wanted to just say that the problem of modeling how energy is actually used in a data center is non-trivial. I mean, it's non-trivial anymore, because while in the past we had a one-to-one mapping between, for instance, users and the resources required for their actual workload. For instance, one website, one server, many users. So more users equals more effort to the server. It was pretty easy to quantify the amount of energy required for this. However, in cloud systems, you have a masking. You have actually these data centers, and you use virtual machines, you use containers, etc. And so basically you need to take into account that one single service may actually be not really user dependent, but more likely how many servers you allocate to this data center in order to grant, for instance, flexibility, elasticity.
Do you hear us?
So the idea is that with cloud systems, you do not actually have it's not easy, because it's difficult to derive a formula that maps user, for instance, number of users with the resources needed for a service to be up.
How looking my words, flexible is the cooling system? How quickly can you adapt cooling to demand? If you're migrating workloads as they come and go, is the cooling something that's going to be able to move really quickly over time, or is it something? Do you know cooling has inertia and how quickly it can adapt to the if the empress knows?
My information, because it's my first month in postdoc, so I do not have enough information, but
So Leo wrote something. So he said that for, I guess, 1 hour for processing, your carbon CPU processing, sorry, your carbon emission is 15% for the technical stuff, which I understand as people, yeah, and 85% for equipment And 40% of this 85 is manufacturing. So overall, what do you have? It's like 50% total of operating costs for energy, Leo, more or less, give or take. Yes, yes. Yeah, so the point that he is making is that the people and the manufacturing should be included in the energy cost. And I think that the EcoInfo tool does that. I saw there is an option for that. Yeah, I agree. He says that energy consumption is difficult. I guess we are more than one in this room concerned with this point today. So if there are no...
Regarding energy consumption, the useful question is more, how does it change when you adapt your strategy? If you know you're gaining energy, it's already a good point.
So I guess you should have your definition of energy efficiency to start with.
Yeah, but when you're looking at a delta, like if you know that adding a workload, if you have two workloads on two servers moving this way,
yeah,
you know you're gaining even if you have trouble quantifying it. And maybe we should look more at the shift in energy consumption than the total, which is really hard to estimate.
Yeah, I guess the shift is there are two separate problems. Like one is optimization and the other one is if you need to decide, do I want to deploy this or not? Maybe you want the
if you want to know if
actual,
if it's a go no go question,
yeah. So they are two separate problems probably. Or
May I ask a question?
yes.
Yeah.
Okay, so I worked a little bit on green AI last weeks, and I believe that I'm not sure that optimizing data center is the only way to go, because data center could be seen as a kind of bandwidth to get compute resource, but actually the true problem is what you want to compute. So if your algorithm are unoptimized, consumes a lot of energy, like large language models or this kind of stuff, if you don't optimize the underlying model, of course, you will require a lot of compute resource. So if you truly want to save energy, of course, you want to limit the number of data centers, but the data centers are just here to fulfill an existing demand. And so I believe that the right way to handle the problem is rather to minimize this demand by designing optimized algorithms, by having wise usage of AI typically, and especially for training, but not only for training, because inference costs a lot too. And also an aspect that you didn't cover is where the data center is run, because depending on the country, you do not rely on the same kind of energy. So for example, if you run your computing tasks in Canada or in France, for example, it won't rely so much on fossil energies. But if you run your compute in the United States, for example, it will be typically coal, oil, these kind of things. And so this is an important aspect you have to keep in mind.
Yeah, so Google rely on 7 nuclear plants to feed AI.
Another question, because all the strategies we saw, none of them deal with the manufacturing cost, which is one of the big costs. Are there strategies that you know of that work at seeing how we can reduce going forward the manufacturing costs by changing up the strategies within data centers? Or is that just something we know we're going to have to change everything every 7 years and there's not much we can do about it? Are there any strategies that you know of in that direction?
My focus is just in these 3 strategies in my first month of postdoc. So I didn't have any.
Leonardo points out that one that might exist is adapting the workloads based on their needs to push low need workloads on older equipment rather than replacing them in the chat, but that's okay.
So I had another, yeah, there is this idea that Marco wrote about moving computation, AI computation in data centers where you might rely on a better energy source, but then I think that this opens up another question, and how much do you spend in moving things around, especially if you have these large models, and how do you measure that? How do you measure the cost of moving things around? And so it becomes a never-ending problem. I think it's very complex. Okay. And the last point Marco is making is about reuse. And these cuts or makes more efficient the use of resources that you did in the manufacturing phase. And as Leonardo was saying, that accounts for like 30% of your, it's 40 of 85%. So yeah, it's a big chunk of the carbon emission of associated to the life of this device. So I guess we have a lot of open questions all around. So thank you, Fadel. I think we can wrap it up for today. And